Hello everyone. In this video, we are going to see Unit 3 padding, stride, multiple input and multiple output from deep neural networks. So I am Lavanya Jayaraman, Assistant Professor of Computer Science and Engineering in Sri Venkateshwara College of Engineering. Let's get started. Padding. Padding refers to the process of adding extra pixels around the borders of an input image before applying a convolution filters. So most commonly these added pixels are zeros, which is why the technique is called zero padding. Let's first understand what happens without padding. When no padding is used, the convolutional filter can only slide over the positions where it completely fits inside the image. As a result, the pixels near the edges are used fewer times than the central pixels. Because of this, the output feature map becomes smaller than the input image. Each convolutional operation reduces the spatial dimensions, and as we stack more convolutional layers, the feature maps shrink rapidly. This can lead to loss of important information, especially from the borders of the image. Now, let's see what happens with padding. When padding is applied, extra pixels are added around the image borders. This allows the convolutional filter to slide over every possible position, including the edges and corners. As a result, the spatial size of the output can be maintained or controlled, often kept the same as the input. Padding helps preserve edge information and prevents excessive shrinking of feature maps and allows deeper networks to be built without losing spatial resolution too quickly. This is why padding is especially important in deep convolutional neural networks, where multiple convolutional layers are stacked together in the deep neural network is important for padding. Types of padding in convolutional neural network. There are mainly two common types of padding used in convolutional neural networks. First one is valid padding and then second one is same padding. So first let's talk about valid padding. It is also known as no padding. In valid padding, no extra pixels are added around the input image. The convolution filter is applied only to the regions where it fully fits within the image. Because of this, the output feature map becomes smaller than the input. Only the valid part of the image is considered during convolution. For example, when the padding value is 0, valid padding is used by default. Now let's move on to the same padding. It is also known as zero padding. In same padding, zeros are added around the border of the input image before convolution. This allows the filter to slide over the edges as well as the center of the image. When the stride is equal to 1, same padding ensures that the output size remains the same as the input size. It also helps to preserve important information at the edges of the image, which might otherwise will be lost. Let's take a simple example for padding, zero padding. So assume that we have an input image of size 5 cross 5 image, a filter of size 3 cross 3 and a stride of 1. So if we use no padding, the filter cannot fully cover the border pixels. So the output feature map is calculated as output size equal to 5 minus 3 plus 1 into 5 minus 3 plus 1 equal to 3 cross 3. So with valid padding, the output becomes smaller than the input. Now let's consider same padding, also called as a zero padding. So in this case, we add zeros around the border of the input image. It allows the filter to slide over every position including the edges. This way, the output feature map keeps the same spatial dimensions as the input, preserving important edge information. Then other types of padding. Full padding. Full padding adds the maximum number of pixels around the input so that the convolution filter can slide over every possible position even beyond the original borders. With full padding, the output size actually becomes larger than the input. This type of padding is rarely used in practice because it increases computational cost. Next one is reflect padding. So in reflect padding, the border values of the input are mirrored to create the padding. For example, in one dimensional array, 3, 4, 5 becomes 4, 3, 3, 4, 5 and then 5, 4 after padding. This method preserves edge patterns better than zero padding, making it useful when edge information is important. Next one is replicate or repeat padding. So replicate or repeat padding which extends the border pixels outwards by repeating their values. For instance, 3, 4, 5 becomes 3, 3, 3, 4, 5 and then 5, 5. This technique ensures that the edges are continued, which can help prevent artificial discontinuities introduced by zero padding. Circular padding, which also known as wrap around padding. In circular padding, the values from one side of the input are wrapped around to the opposite side. Instead of adding zeros or mirroring values, the padding comes from the other end of the data. For example, if the input values are 3, 4, 5, after circular padding, it becomes 5, 3, 4, 3, 4, 5. So here the input values are 3, 4, 5 and the output becomes 5, 3, 4, 3, 4, 5 and then 4, 5, 3. So this technique treats the input as if it is were a circular or periodic. So circular padding is commonly used in signal processing and frequently based applications where data naturally repeats or wraps around. So next one is constant padding, also called custom value padding. In constant padding, the input is padded using a fixed constant value which does not have to be zero. The padding value is chosen based on the specific problem or data requirements. For example, the border may be padded with values like 1, -1 or any other constant instead of zeros. This allows more flexibility compared to zero padding and can be useful when a zero introduces unwanted bias or artigraphs. Effect of padding on convolutional output size. So padding, usually denoted by P, which refers to adding extra pixels. So more often zeros around the borders of the input image. By doing this, padding increases the effective size of the input before the convolution operation is applied. Let's the original width of the input image be W. When padding of P pixels is added to both the left and right sides, the effective width becomes W effective equals to W plus 2P. This happens because padding is applied symmetrically on both sides of the image. As a result, the convolution filter can slide over more positions including the edge regions. Padding helps preserve spatial dimensions, which ensures that boundary information is not lost and prevents excessive shrinking of feature maps as we go deeper into the network. In deep convolutional neural networks, This makes padding a crucial design choice for maintaining stable and meaningful future representations. Example for padding. So, effect of padding on convolutional output size. Let's understand the effect of padding using a numerical example. So, given is a input size 5 cross 5 and filter size 3 cross 3, stride 1, padding 1. The general formula for calculating the output size of convolution operation is output size equal to L into W minus K plus 2P divided by S whole to the plus 1. So now let's substitute the given values into the formula. We are going to substitute the values directly in the output size formula. So 5 minus 3 plus 2 into 1 divided by 1 plus 1 equal to, so 5 by 1 plus 1 equal to 5 plus 1 equal to 6. So this means the output feature map has a size of 5 cross 5. So when padding P equal to 1 is used with a 3 by 3 filter and stride 1, the spatial dimensions of the output remain the same as the input. So this is why this configuration is referred to as a same padding. It preserves the input size while still allowing the filter to process edge pixels effectively. Why padding? So why padding is used in convolutional neural network? Padding is used to add extra pixels around the border of an input image in order to prevent the image from shrinking after convolution. Without padding, each convolution operation reduces the spatial dimensions, which can quickly lead to very small feature maps in deep networks. Padding also helps to preserve important edge and border information. Pixels near the boundaries contain valuable features, and without padding, these pixels would contribute less to the output or be completely ignored. Among all padding techniques, zero padding is the most commonly used. It is simple, efficient, and works well in most practical applications. Most importantly, padding helps to maintain the size of feature maps, making it possible to stack many convolutional layers without losing spatial resolution too quickly. This is why padding plays a crucial role in building deep and effective convolutional neural networks. Next topic is stride. So what is stride? Stride is the number of pixels by which the convolution filter moves across the input image. So in other words, it controls how far the filter shifts at each step while scanning the image. For example, a stride of 1 means the filter moves 1 pixel at a time, which covering every possible position. So a stride of 2 means the filter jumps 2 pixels at a time, skipping some positions. So effect of stride on output size. So stride has a different impact on the size of the output feature map. So when a large stride is used, the filter overlaps less with previous position, resulting in a smaller output feature map. When a smaller stride is used, there is more overlap between filter positions, producing a larger output feature map with finer spatial details. Stride in pooling layers. So stride is not just for convolution, it is also used in pooling layers. So in pooling, a window like 2 by 2 or 3 by 3 slides over the input feature map. The stride determines how far the window moves each step. So a larger stride means the window moves further, more down sampling and smaller output feature map. A smaller stride moves the window shorter distances, which leads to less downsampling and a larger output feature map. For example, 2 by 2 max pooling with stride 2, which takes the maximum value in each 2 by 2 patch and moves 2 pixels each step. This reduces the feature map size by half in both width and height, which keeping only the most important features. So stride in pooling, which controls how aggressively we reduce spatial dimensions, balancing computation efficiency and feature retention. Convolution output size formula. So to calculate the size of the output feature map after a convolution operation, we use the formula like output size equal to W minus F plus 2P divided by S plus 1. So here W is the width or height of the input image and F is the size of the convolution filter or kernel and P is the amount of padding applied to the input and S is the stride which controls how far the filter moves at each step. This formula shows how padding increases the effective input size while stride controls how densely the filter is applied. By adjusting these parameters, we can precisely control the spatial dimensions of the output feature map. Example for stride 1 and stride 2. So let's see how stride affects the output size with a simple example. Input 7 by 7 image. So and filter size is 3 by 3 and padding is 0, stride is 1. So we calculate the output size using the formula output size equal to W minus F plus 2P divided by S plus 1. Substitute the values in the formula, we will get output size equal to 7 minus 3 plus 0 divided by 1 plus 1 equal to 5. So the output feature map is 5 by 5. Because the stride is small, the filter moves 1 pixel at a time, producing a more detailed feature map that captures more information from the input image. So next example for stride 2 given is input size is 7 by 7, filter size is 3 by 3, padding is 0 and stride is 2. Using the output size formula, output size equal to L into 7 minus 3 into 0 divided by 2 plus 1 equal to 4 divided by 2 plus 1 equal to 2 plus 1 equal to 3. So therefore the output feature map is 3 by 3. This shows that with a large stride of 2, the output size is smaller compared to stride 1 due to the filter moving in bigger steps. So large stride which takes the smaller stride in convolutional neural networks. So finally the stride which controls the step size of the convolutional filter as it slides across the input image. So as a larger slide means the filter moves in bigger steps while a smaller stride moves the filter more slowly, covering more positions. Increasing the stride reduces the output size because fewer positions are covered and it also reduces computation since fewer multiplications are performed. Stride is an important hyperparameter in CNN design as it directly affects both the spatial resolution of future maps and the computational efficiency of the network. Next topic is multiple input. So multiple input in convolutional neural network. In CNN, the input images can have multiple channels, also referred as a depth. For example, a standard color image has three channels: red, green and blue. We will call it as RGB. Each channel is represented as a two-dimensional matrix with dimensions height into width. When a convolution filter is applied, it operates across all channels simultaneously and combining information from each channel to produce a single output feature map. This allows the network to capture complex patterns that depend on combination of channels rather than treating each channel separately. How filters work with multiple input channel in CNN. When an input has multiple channel, the convolution filter are no longer two dimension, they became 3D tensors. The dimensions of a filter are f into d, which means f cross f represents the spatial size of the filter, height and width, and d represents the depth, which is the same as the number of input channel. Each filter spans all input channels, meaning it looks at every channel simultaneously. During convolution, the filter multiplies its weights with the corresponding value in each channel and then sums across the depth dimension. The result of this operation is a single 2D feature map. This mechanism allows each filter to capture patterns that combine information from all input channels such as edges, textures or color combinations in RGB images. Multiple outputs. Multiple outputs in convolutional neural networks. So in CNN, it uses multiple filters called also called as a kernels in each convolutional layer to extract a variety of features from the input. Each filter produces one 2D feature map which can be thought of as a single output channel. When a layer uses K filters, it generates K feature maps which are stacked along the depth dimensions to form the final output of that layer. This allows the network to capture different types of patterns simultaneously, such as edges, textures and color combinations, giving the next layer richer and more complex representations to work with. Multiple input and output dimensions. So in input, the input has dimensions height into width into channel. For example, the color image of size 32 cross 32 with 3 channels RGB has a dimension 32 cross 32 into 3. And a filter, so each convolutional filter has dimensions filter size into input channels. So for instance, a 5 cross 5 filter applied to an RGB image has the dimension 5 into 5 into 3. And a number of filters, the number of filters which determines the number of output channels. If a layer uses 62 filters, means the output will have the depth of 64. So the output feature map, which is after applying all filters, the output feature map has a dimension height into width into number of filter. So in this example, using 64 filters on the 32 cross 32 into 3 input with stride and padding such that the spatial size reduces to 28 cross 28. So the output would be 28 into 28 into 64. This structure allows CNN to capture multiple types of features simultaneously, stacking them depth-wise to feed richer information to the next layer. Okay, so why multiple filters are used in CNN? In each convolutional filter in a CNN is designed to learn a different feature from the input, such as edges, textures, colors or shapes. So using multiple filters allows the network to capture a diverse set of features simultaneously, which improves its ability to understand complex patterns in the data. Multiple input channels like the RGB channels in a color image let each filter combine information across different dimensions. When we apply multiple filters, we provide multiple output channels, also called feature maps, stacked along the depth dimension. This depth-wise stacking of features is one of the key reasons why CNN are so powerful in feature extraction and representation learning.